We are continuing a series of videos on conservative mechanical systems. We have already discussed the theory of conservative systems. That is, if we have some forces acting on an object, and those forces can be written as the gradient of a scalar function. I'm calling my scalar function v, and v only depends upon spatial variables, that is, location of my object. Then some really cool things happen. So first of all, the work done by these forces on the object as the object moves along some path from point A to point B, that work is path independent. That is, doesn't matter which path you take in going from point A to point B, you always get the same amount of work. So you can go along some crazy paths here, and always it's the same amount of work. That is, the work in going from A to B only depends upon the endpoints, A and B. In particular, the work in going from A to B, it works out really nicely that the work is just going to be this function at A, VA minus VB. Where V, again, is this very special function whose negative gradient is equal to that force. And further, the work energy principle tells us that the work in going from A to B is the kinetic energy at B minus the kinetic energy at A. We can make the substitution, right? We can take VA minus VB, which is the work, put it right into there, rearrange terms a little bit, and boom, we get a little expression like this. It says TA plus VA is equal to TB plus VB. So we got this quantity at point A is equal to the same quantity, T plus V, at point B. So this quantity, T plus V, kinetic energy plus this potential thing, you can call that the total energy, total mechanical energy if you want to be a little more careful. That thing is conserved. Right? T plus V, kinetic energy, plus V, this function whose gradient is equal to that force, we'll call it a potential if you will, that potential, that thing is going to be conserved. It's something it's a quantity that's not changing as the system changes. All right, so let's go back to the pendulum. What do we have here? We've got a mechanical system. We've got some forces acting on it. It's doing its thing. And let's consider those forces. I'm going to pause the pendulum right around here someplace. So the question we'll start off with is, what are the forces acting on the object? The object in this case is this mass right here. Okay, so pause the video, draw yourself a nice free body diagram perhaps, and we'll get back on the other side. All right, so we'll start with, assuming we have a few forces on this body, we'll start with the weight, right? Gravity's tugging down on this. The Earth is tugging down on the object, and we'll call that weight W. And what else? If it was only weight, then the object would just fall straight down. So there has to be something to pull it along this curved path, right? And that something, of course, is the tension in the rod. So the tension in the rod is pulling this away. Now I want to switch our perspective to the work energy principle, right? Get away from F equals ma. Let's look at work and energy. And we'll ask ourselves, what can we say about the work done by this tension force? There's T. Is it positive? Is it negative? Is it zero? What can we say about it? Again, pause the video, think about it, and then come back. Well, remember that the path of the pendulum is always a constant distance from this pivot point. So therefore, the path of the pendulum is along this circular arc right here. Circular arc is sort of bouncing into a few things here. So, but what's important is that this tension force is perpendicular to that circular arc. The path is that circular arc. The tension force is perpendicular to the path, so therefore the tension does no work. So again, from our work and energy perspective, we're going to ignore the tension. It does not play a role when we take this perspective on the problem. Now in contrast, the weight does do work, right? The weight is not perpendicular to the path. It's not perpendicular to that circle, right? And when the pendulum is heading downward, the weight is also pulling downward, so it does positive work. When the pendulum's heading upward, the weight does negative work. And the really cool thing about the weight is, well, let's rewrite the weight. The weight is what? mg in the minus j hat direction, if j hat is positive upwards. And what's really cool about the weight from our work energy perspective is that this weight force can be written as the gradient of a potential, right? We've seen this before. This potential is m times g times, if y would be our vertical coordinate for position, then it's m times g times y. So this is awesome. This is telling us that our system is conservative. That is, we take this quantity, t plus v. The t is not that t, by the way. That one was tension. This t is kinetic energy, which is 1/2 m times speed squared, plus the v, which is m times g times the height, the elevation, I'm going to call it y. This thing is constant. It is conserved along trajectories of the system, along solutions of the system, right? And that's interesting. So let's go back to the pendulum. We'll unpause it. And there it goes, yes? So as it's going, it goes way up to the top, it comes back down, swings again. And up here in the upper right-hand corner, we're going to create some bar charts here. The first one is the kinetic energy. It's the 1/2 mass times speed squared. And again, it's a little bar chart right here. So when it's up at the top, it's almost stationary. It's going to be 0. But as it swings down, we pick up a lot of speed. We get a lot of kinetic energy. And you can see that energy, or kinetic energy, registered in this little bar right here. See, there goes the energy again. Woo! Yeah? There's the 1/2 times mass times speed squared. And then we get this other thing, the potential. That's m times g times y. Let me hide the kinetic energy for a bit. Let's put the potential in. That's the green bar, right? Y equals 0 is going to be where the pivot is. So when the mass is above the pivot, when we get y positive. When it's below, we get y negative, right? So here we are, we're well above the pivot. We're getting maximum potential energy. And then we go down here, it becomes negative and positive again, right? So we put both of those, let's look at both of those terms together now. So we see an exchange between that potential energy and the kinetic energy, right? When one's big, the other one's small, right? When that kinetic energy gets real big, the potential energy goes negative, right? But that quantity, kinetic plus potential, the T plus the V, that has to be conserved. So if I take the orange bar and the green bar and add them up together, they should give me a sum, which I'm going to plot next. And that sum, if things are right, that sum should remain constant, right? So here's that potential. There goes the potential. It's being exchanged for the kinetic, but the total energy, the red bar, remains the same. Right? If I just have one of those, just the kinetic energy, the sum is this. If I just have the potential, the sum is that, right? But when I add them both together, yeah, that's constant. That's what we see. Now, a real interesting thing in here is that whenever this thing comes to a stop, there it is, it's coming to a stop right there. All that kinetic energy, all that energy is potential energy, right? And potential energy only depends upon the height. So every time it comes to its highest position, it must come to the exact same height. Let's mark it right here. So here we are at the very top here. Boom. That's my closest mark of that point up there. Let me try to get it on the other side as well. Up to the highest point. Boom, right there. And you'll notice those two heights. Let's look at those two heights. Oh, let's look at this right now. It comes back to the exact same point, right? And watch it comes back again. It'll come back to the exact same point. Right there. Right there, right? And one thing you'll notice, let me pause right there. Those two heights, those two highest parts, when it swings up and upward from the left side and upward from the right sides, those two maximum points are the exact same location, right? And you notice this thing never, unpause, it never goes over the top, right? It never goes over the top and onto the other side, because in order to get onto the other side, it has to go higher, but it can't go higher because it doesn't have enough energy to go higher, right? So this thing, if it's purely conservative system as it is, if we don't have any friction or any air resistance, as the simulation does not have, then this thing will always oscillate back and forth between the same 2 points. This is a characteristic of a conservative system such as the pendulum. And we'll end this video there. We'll see a more interesting system in the next video. A little more system that has some more rich dynamics. All right, over and out.